Hello everyone, and welcome to the last chapter of our dynamics about impulse and momentum of rigid bodies. So if we have a little talk on the particle and then the definition of how we are going about the impulse and momentum. So let's start with the equation of second law of Newton. We know sum of F is equal to ma. So force is equal to mass times acceleration. Now in this equation, if instead of A you put dvx over dt, you ended up as the equation, and then you cross multiply it, you can get ended up as this equation. Sum of f of x dt is equal to m dvx. Now if you integrate this equation, you ended up as this equation. So in this equation, if you bring the Vx to the other side, or what you could say this is a linear momentum. Linear momentum in the second state is equal to linear momentum in the first state plus the impulse or impact, which is force times the time. Now in the idea of particle, we said that okay, if you are coming with your car and then you are hitting a concrete wall, now this car has a momentum, and that momentum is mv. Now when it's hitting the wall, mv translated to a force here with the time, which is F delta t. Now whatever if the time is more, if delta dt or delta t is higher, your impact force will be lower. That's why we use elastics objects look like bumpers on the car. So now moving from there to rigid body, how things are changing. So in rigid body, if you're looking to one rigid body like the representation here, at the point G, you have several types of momentum. One, you can have momentum on the X, which is what we call it mvgx, and then momentum on the Y, which is mvgy. Now on the rigid body, again, you should have you could have a rigid body look like this pen, which is simply moving. Now you have this pen is moving and rotating. So in such cases you have more momentum, right? Because if you look at here, linear momentum, this is going on the X or on the Y, but as it's going, it's rotating, you ended up with more momentum. So linear momentum are mvx and mvy. We put them at the center point G, and then what we have here, we have the rotational part of it, which is ig omega. How we come with the ig omega, and then so that's actually types of angular momentum. So it's not a linear momentum, it's due to rotation. Angular momentum from particle, we remember that angular momentum used to be r times mv. Now in total you can say angular momentum is equal to r times mv plus ig omega. If you have a point, which that point look like a point P here. If you want to calculate momentum, if you want to calculate angular momentum about point P here, so remember H is a representation of angular momentum. We can say HP is equal to ig omega, what we have here, which is ig omega. Then you have two terms. One term of mvgx, which will be multiplied by this distance, which is y bar. In this case, about point B, this is going to go clockwise, so that's why we put a negative here. And then the last one is about on the y, which is mvgy. The perpendicular distance will be the x bar. So we can say ig omega minus mvgx into y plus mvgy into the x. So you don't need to memorize any equation. If such a cases where we see them, we can actually figure it out. But what I want to tell you, if the point P is in a different location, like assuming that point P is here and then your G is here, now your calculation will be completely different. So now in this case we have ig omega, and then this is mvgx, and then we have mvgy. If the point P is here, in this case, x is going to go counterclockwise, but the y is going to go clockwise. So the sign here will switch. But we don't need to be worried about that. But this is just an example of showing you how that equation ended up. So in the equation we show you up there about force, we can actually multiply that by r. That's what we did in the particle. And we ended up with the equation for angular momentum. But I want to show you what is sum of moment. Again, moment is torque. We want to find sum of moment about point G is Ig d omega over dt. So how I ended up with this equation? If you remember from kinetics, we know that sum of mg is equal to Ig alpha, where the moment about point G was Ig was, we call it moment of inertia, mass moment of inertia. Alpha is the angular acceleration. Now, if you get this equation and then you integrate this equation from both sides, if you integrate this equation from both sides, before I do the integration, I can replace alpha. I already know that alpha is d omega over dt. So alpha is angular acceleration, and omega is angular velocity. So if I integrate this equation, I'm going to end it up as, if I replace d omega with dt, alpha with d omega with dt, I'm going to have equation like this. Then you could do what you could do. You could integrate this equation from both sides. Then the resultant of this would be equal to integration of sum of m about point G is equal to Ig omega 2 minus Ig omega 1. So we ended up with the different equation. So in this equation, you can actually you can say you can keep this one in this side and move the other one to the other side. But you could say again, there's a dt here. My apology. We are integrating with respect to time. So you are cross multiplying this. Before you do the integration, you have to cross multiply this, and then you ended up at sum of moment dt is equal to this one. So what does this mean? This means the moment that you apply with the t on the integration of it is the difference between Ig omega in the second minus the first one. When we have rotation about fixed point, we can actually prove that if you do rotation about fixed point, you can say sum of moment about point O, which is fixed point, is IO alpha. And then again, if you already have this from kinetics, if you integrate it, you ended up at this equation. HO, so the rotation about O is IO omega. And in the case of where we are in a general motion, so this is going to be when we in general motion, we have HIC is equal to IIC omega. So HIC is angular momentum about, so IC was instantaneous center for zero velocity. I can say that about center of zero velocity. IIC is moment of inertia about center for zero velocity. Omega is the angular acceleration. So let's summarize the equation. If we summarize the equation, we can say mvgx2 is equal to mvgx1 plus the impact that's happening due to the force on the direction of x. Now we can say the same thing on the direction of y. And the last equation is Ig omega 1 is equal to integration of sum of mg dt, Ig omega 2. This is actually this equation. There's no new equation, just you have a recap of it. That's that equation, and the other equation we just proved it in the beginning. So let's do one example. In this example that I want to solve is just to erase this repetitive. So in this example, we have a cylinder showing has a mass of 6 kilogram, which rotates about fixed point of A. It's attached to a cord which is wrapped around a 20 kilogram disc. So we have the cylinder is here. Cylinder is down here, which is 6 kilogram, and disc here is 20 kilogram. Now the moment of inertia of the disc is given to us. If the cylinder is initially moving downward with the speed of 2 meters per second, so we have the initial speed of point P, which is point P here is the same as the cylinder. So we can say point P is the same as the speed of cylinder. In the beginning is 6 meters per second. 2 meters per second. Determine the speed after 3 seconds. So they gives us a time. Because it's the time, then we can figure out that we need to use momentum. So by just looking in this problem, what we can figure out, do you see any motion in X? Do you see any motion in Y? Like if I look at just simply, if I just look at the disc, I can see something. If I look at the cylinder, I can see something else. If I look at the cylinder, cylinder is moving on the Y. But if I just look at disc, I could just see disc has a rotational types of motion. So by giving us the 2 meters per second here in the beginning, because you see we have something like this. Down here I have velocity is equal to 2 meters per second. And this is R. You have omega, which is going clockwise. Then you can say V is equal to R omega. Because just rotation about fixed point, right? And then we have 2 is equal to radius is 0.2 omega. From here, omega will be 10 radian per second. That's how the calculation we did. We found the omega 1 in the state 1. Now, if you want to go to state 2, to omega 2, we need to find, again, the velocity of the point, and then how can we go about that? So let's just consider what forces we have in this case. We have different forces. Down here on the disk, we have one force is going up all the Y, another force on the X. So I'm going to call this one AX, AY. I have the force of the center point of the gravity, which is 20 times 9.81. We have the tension T that's going down. Again, if you look into the cylinder, on the cylinder you can see a tension and the gravity. So that's how it looked like in the cylinder, but in the disk, that's what we have. So if I want to go about this problem, the best way I go is just rotation about fixed point. Rotation about fixed point, what equation I can use? I can use this equation, that IG omega 2 is equal to IG omega 1 plus integration of sum of moment about point G dt. Now IG omega 2. So IG is given to me 0.4. Omega 2 I don't know. I want to find it. Omega 1 is given as 10. Actually, we found it from this calculation. 10 radian per second. We have the IG again. And why we put negative? Because this is clockwise. Now on the moment about point G. If you want to calculate the moment about point G, you have three forces that are already on the point G. We just left off with T. So that T will be times the radius, which is 0.2, is going clockwise. So it will be minus T times 0.2 dt. The time of integration is from 0 to 3 seconds. So after we finish our calculation, we find the relationship. This relationship is between omega 2 and the T, the tension. But how can we find the tension? So let's move into the cylinder. In the cylinder, what forces we have? We have a force of T, we have the force of 6.981, and then we actually need to do more calculation to get into the and getting to the bottom of this problem. Now, if you look into this, you can actually use like what types of motion you have. Let's list the equation. We have sum of m. Could just use it as this: m vg x2 is equal to m vg x1 plus integration of sum of f of x dt. Then you can repeat the same equation for y. M vg y in the state of 2 is equal to m vg y in the state of 1 plus integration of sum of f of y dt. Now the last equation was about rotational motion. Ig omega 2 is equal to Ig omega 1 plus integration of sum of moment dt. In this object, this cylinder doesn't have any motion on the x. There is no motion on the x, because if I draw the diagram, mvgx is 0. On the y, we have a motion which is going down. You can put it like this: mvgy and then ig omega, no ig omega. This is 0. No, it doesn't rotate. So we ended up only in the direction of y. So in the direction of y, what we have? So I need to use this equation. From this equation, I'm going to get mass of cylinder, which was 6 kilogram, into next one is Vg2 that I don't know it. I'm going to call this one just I'm going to call that V2. And then moving forward, I have V2 is equal to m, again 6. In the beginning, this was going with the velocity of 2 meters per second. So I put 2 meters per second here. Remember, I'm considering my direction this way for y, just for simplicity, because everything going down that way. Plus integration of t is 6 times 9.81. I mean summation of f of x of y. This will be this minus t dt from 0 to 3 seconds. So if you simplify this equation, you're going to find 6v2 is equal to 12 plus, okay, integration from 0 to 3 of this. So meaning that I need to multiply this by 3. That's it. So 6 into 9.81 minus t, everything times 3. Or you can say from 0 to 3, then you substitute 3. So this is one equation. I'm going to show this with the star. And the other equation we have was here. Again, the smarter way for here was we just simply, instead of omega 2, we replace that with V2. And we already know that relationship. And we already know that V2 is equal to R omega 2. So you ended up with one equation here and another equation here. Then using these two equations, you can actually solve it, and then you can find both V2 and T. So, and then I'm going to show, this is the equation with 2 stars. So use the equation with 1 star with 2 stars to find V2 and T. You have 2 equations and 2 unknowns, and you can simply solve it. So in the next lecture or the next talk, I'm going to talk about conservation of momentum. So if there is no force in between, or something like, for instance, we use this a lot for impact, when 2 objects hit each other and then they actually move away. It doesn't matter, we lose energy, we don't lose energy, whatever the impact, as long as the system is isolated and then no other force is coming in between, we can say conservation of momentum. Like assuming that I'm bumping 2 hands together, this is a conservation of momentum. Now again, if as I'm bumping, if I have an extra force from somewhere else, you cannot say that conservation of momentum. Or you have a moment from somewhere else, you cannot say that. But because those, like mainly they are happening in an instant, that we don't have a t to have external force or something like that, right? So when we say external force, because we don't have a time, the time is very small, then you cannot actually apply other force. It's just the force of impact or the whatever. So in such cases where we have impact, we can say the summation of force is 0. Then you can say mvgx before the impact is equal to mvgx after impact. Same thing. mvgy before impact is the same as mvgy after impact. For angular momentum, we can say sum of hg before is equal to sum of hg after. So angular momentum conserved before and after impact. So if you have a fixed point, we can state the same thing. Sum of h about 0.0 before the impact is equal to sum of h about 0.0 after impact, where O is the point of rotation. Now, in this case, this problem, they give me a bullet with a rod. So let's look at this problem to see what is going on in this problem. There is a 5 kilogram slender rod, which shown in this page, is pinned at point O. Then this is actually initially as rest. That's a good news. So everything in the beginning is 0 on the rod. But there is a 4-gram bullet which is fired into the rod with a velocity of 400 meters per second, as shown, with the angle of 30 degrees. Now determine the angular velocity of rod just after the bullet embedded in it. So we know that what's happening is that after impact, the bullet is going to go inside that. You don't actually need to consider anything about bullet after, because bullet is like 4 gram. We are talking about 5 kilogram. So what we could use in this case, we need to think about what types of motion we have, and then how many unknowns we are looking for. After impact, like before impact, there is just one thing is moving, and that thing is the bullet. But after impact, we have the motion of the rod, and that motion of the rod has the Vg on it, and has another component which is Ig omega. So we have Vg and we have Ig omega. Again, a reminder that H is R cross with Mv plus Ig omega. So let's look at the before impact. What's happening to the bullet? The bullet has a velocity of 400 meters per second. We have a point of rotation here. Now we want to find angular momentum. So what is happening? So let's look at here. This is the point of rotation O, and bullet is coming like this. If I want to do angular momentum about here, again, I go back to the lecture that we have before. You need to break down the 400 meters per second to 2 components. One component in X, one component in the Y. So this will be on the X, will be 400 cosine 30. On the Y will be 400 sine 30. Which one of them create rotation? I believe this one doesn't create any rotation. The only thing that creates rotation is 400 cosine 30. So in the equation that we have R cross with MB. Again, this is cross. Cross means perpendicular component. This is cross product. In cross product, we always do perpendicular distance. So perpendicular distance would be 400 cosine 30 times the distance from here to here, which is 0.75 meters. So from here to here is, and that comes to our calculation. We have the R, which is 0.75. The mass of the bullet is R cross with MB. The mass of the bullet is 0.04 and 400 cosine 30. And how we got 400 cosine 30? From here. Because that's just the perpendicular component. Before the impact, before rod is not moving. So H of rod is 0. If I give you the same problem and I say that the rod is moving with the velocity of 3 meters per second, it's going to be easy. You can say, okay, the rod has the velocity of 3 meters per second. Then you can calculate all those. The R for this case, because I give you the velocity of center point, Vg of rod is 3 meters per second. Then you can say 0.5, which is the center of mass of this rod, from here to here is 0.5 times that. And you can go ahead from there. Plus the omega too. We need to consider omega as well, Ig omega as well. So let's consider the case after. Okay, when we consider the after, the Vg, we don't know it, right? Vg of, again, there is R and VGB. B means bullet, B means bullet, R means rod. Now, for the rod, we have Rg. Okay, Rg is from here to here, which is 0.5 meter. And then cross with Mr VRG. And we don't know VRG, by the way, after the impact. RG, we know it. This is actually 0.5 meter. Mr, mass of rod, is given to us as 5 kilogram. So this is 5 kilogram. Ig omega. Ig, I don't know it, but I can simply calculate it. Ig is 1/12 ml to the power of 2. Then once you finish your calculation, you find 0.42. So the value for this is 0.42. And then omega for the rod, right? What is omega for the rod? Now, omega for the rod, if you look into this picture, you have velocity of g, and then you want to find omega. So what will be the omega? Omega is, you can say VRG is equal to RG times omega. And RG is 0.5. Now, in this equation, I can say, I need to find what is the question asked me, determine the angular velocity. So I'm interested in angular velocity. Then I can say omega is equal to Vg divided by 0.4, which is 0.5, which will be, I can say omega is equal to Vrg over 0.5. Now let's look at the equation. HO, the bullet, after the impact, again, bullet doesn't have anything when it comes to complete stop. The problem with this, the mass is too small, like 0.004. If you multiply this, you're going to end up as nothing in this calculation. That's why we use a 0, like 4 gram compared to 5 kilogram, which is nothing. Now in this case, this is actually the beginning, that's 0.5 times 5. And then instead of Vg, we put 0.5 omega from this equation. Plus Ig, which is 0.42 from here, and then omega. So we found everything in terms of omega. So if you look into this equation, sum of HO before the impact, we had 1.04. After impact, we have these 3 times each other, which would 125. Omega plus 0.42 omega. From here we can find omega is 0.62 radian per second. So I'm going to do one more similar problem like this. In this case, I have a disc which is hanging from point O, very similar to that rod. Again, is a bullet is coming to it with the angle of 30 degrees. In this question, the question is some sort of both work and energy and impact and momentum. The question asks me that after the bullet go inside the disc, find the maximum angle in which the disc would rotate upward. So part 1 is impulse and momentum. Part 2 is work and energy. So let's start with part 1. In part 1, before we have the bullet is moving. After that, so yeah, before bullet is moving, okay, yeah, bullet is moving, then we don't have anything from anything from the disk. So disk is 0, velocity of disk is 0, omega of disk is 0. Then after the impact, bullet neglected because it's too small. And for the disk, we don't know omega, we don't know Vg. So we use just the same process of explaining the other problem for this one as well. So we know h about point O, which is the point of rotation here. Sum of HO before is equal to HO after. And H itself is Ig omega plus R cross with mvg. Going ahead, so before that, Ig omega is 0. For bullet, if the bullet is coming and rotating, we have more momentum. But in this case, they gives us only the angular velocity of it. Sorry, they're just the linear velocity. So R cross with mv, same problem that as we did before. The component of velocity that create rotation is just this one times the radius of the disk. So the resultant answer would be R, which is 0.15. M, mass of the disk, is given as because before is we have the mass of the bullet. Mass of bullet is 10 gram, which will be like 10 divided by 1000 will be 0.01. And then we have the velocity. Velocity of it is just the perpendicular component of it, which will be 0.15 times 0.1 times 200 cosine 30 before. And for disk is 0 everything, because disk is not rotating before that. Now what is happening after? After velocity, after about 0.0, we can say everything for bullet will be 0 because bullet is too small compared to 15 kilogram disk. Now on the disk I have Ig omega plus R cross with mvg. So after, if I draw the disk after impact, this would look like this. Right after impact, I'm going to have something look like this. Vg is going to be in this distance, in this location again, because look at the rotation about fixed point. The velocity is always perpendicular to the radius. So you can say Vg is equal to 0.15 omega. And that's how we got it here. Now let's put the equation for that. So we know Ig is half of mr square is a disk. Then you can calculate the moment of inertia for the disk. HO after will be 0 for the bullet plus 0.17 omega, and this is coming from Ig omega. We already know Ig is 1.7 times omega plus R cross with mv. So R is 0.15, m is 15, and then instead of Vg we simply put 0.15 omega. So we found the equation in terms of omega. Now we can actually equate this. So sum of momentum before is this much. Angular momentum before is 0.298. And after that we have it in terms of omega. Then you can solve for omega. So far we found omega. If you know omega, you already know Vg as well. So Vg is equal to 0.15 omega, which is going to be 0.15 times 0.5. And the answer for this is 0.075, which we actually calculated here. So in order to find how much disk is going up, we're going to use theory of work and energy. In work and energy, we say sum of T2 is equal to sum of T1 plus sum of U1 to 2. So what does this mean? T stands for kinetic energy in state 2 is equal to kinetic energy in state 1 plus sum of the work is done from 1 to 2. And kinetic energy is half of mvg to the power of 2 plus half of Ig omega 2. So we talked about that in the previous session. So what types of work we have? We have work from gravity, work from spring, there was work from moment, and then work from force. Let's see what types of work we have. For the disk that's going up, we have work of gravity. And then work of gravity was minus W delta Y, and then in this case, your delta Y is how much? So if the disk going up from this place, so the center point will move from here to a point here. Now we want to find how much is gone up. So delta Y will be R, the radius of the first one, minus R cosine theta. And then in order to show R cosine theta to you, I'm going to say this is R cosine theta. You see that? This is R cosine theta. And that's one, the whole one is R. Delta Y is R minus R cosine theta. So you can simplify this. delta y is equal to 0.15 into 1 minus cosine theta. T2 is 0 because we want to find the maximum height before the disk comes to stop. T1, we can actually find T1. T1 is half of mvg to the power of 2 plus half of ig omega 2. Again, we already found vg, which is 0.075. We already have omega, which is 0.5. Now I'm going to put them in this equation. We know ig and m. And then you ended up at T1 as this much joule. U1 to 2 is minus W delta Y. Again, okay, I have it here, minus W delta Y. This is M. This is G. And this is delta Y. When we are going up, your delta Y is positive. But we have the overall work is negative. The reason for that is that because you are going up where the gravity is down. So the force is down, displacement is up. So that's why the work from gravity becomes negative. So if you put stuff in this equation we have T2, which is 0. T1 is this much. Minus 15 into 0.15. And overall, when you finish your calculation, you're going to get theta as 4.33 degrees. Thank you for watching this video. I hope you have a great day.